Everyone, Patricia Worby, Alchemy Therapies here, and part of our ongoing series is in talking to my colleague Dr. Rainer Verweger, and today we're going to be looking at universal numbers because we both believe that mathematics lies at the heart of who we are and how we fit in this universe and our world. So Dr. Rainer Verweger is a bit more of an expert than I am on maths and numbers, so I'm hoping he's going to take us through this in an understandable way. I will be asking questions if I need clarification. So without further ado, take it away, Rainer.
Yeah, thank you so much, Patricia, for the lovely introduction. And as some of you may already know, that I'm a big fan of scaling phenomena. And this, of course, relates to numbers. And we always say that everything in the universe is energy. And then what kind of energy is that? And then we find out it is vibrational energy. It is oscillations, but why is that? It's easy, but we are not pointing to it when we learn about it a lot. A vibration is that kind of movement in nature which requires least energy. And this is why everything vibrates. There's also another reason that everything spins in circles. And that and not only in circles, but builds up spirals. And those spirals, they are arising from things scaling up. Yeah, when you are in a circle and you want to get to the next level, you have to move in a spiral. So one thing is we have the energy, and that's vibrational energy all the time. And then, of course, a vibration always has a frequency. So how often does something vibrate? And then we meet numbers. So it can be 1 time, 2 times, 3 times, and then things relate to each other. So this is how we come into the world of numbers. And there's a little bit we want to talk about today about numbers and how they might scale and how they relate to each other. Before we start, just a few words why I'm so happy to share this knowledge with everyone who wants to watch our video. We live in times that are dramatically changing right now. And in the past, we had this, or we were taught that things may be separated from each other. So we were looking more at closed systems than open systems. And what we learn today and what's important for our future and the evolution of mankind, that's something where we need to learn that they are cycles which are always embedded in bigger cycles. And even the cycles themselves embed smaller cycles, and that everything is connected to each other and communicates, and that life and even consciousness arises from being aware that there is an interaction between these embedded different cycles in time and space. I think this is a very important new thing, and then we learn that everything we do, everything we observe has an impact on everything else. And everything else that happens has an impact on us. And that's fascinating, I think.
Yeah.
And we could say even that life origins from numbers, from the number continuum. And when we look at numbers, then we would say that numbers are just symbols to describe certain amounts. So it may be 5 roses or 5 people. It's the same amount, a different quality, but same quantity. Yeah, but we will later look at prime numbers, and they will also be different quantities, but they also will create another quality. So I explain that later. And numbers are also quanta. So the whole discreteness, to go from 1 to 2, we always have to do a step. We can go to 1.5 and then to 2, but then this is 2 steps. So we hear about those quantum leaps. Yeah, and these are always little leaps that have to be taken from one number to the next, and we can zoom in, we can even go into tens, hundreds, thousands, and go into infinity, but we still have to do that little jump from one to the next. So it's a discrete thing, which is a property of the quantum world. What are we using numbers for? So first of all, for counting, of course.
Yeah.
Yeah, so we count 1 and 2 and 3. And later we will talk about a logarithm or exponential growth. And the logarithm is basically the exponent of something. And why is nature using logarithms? That's because counting is faster. Yeah. When we say 1 to the power of 1, which is 10, and 1 to the power 2 is 100. So counting from 10 to 100 is a long way to go, from 11, 12, 13, 14. But using the logarithm to the base of 10, that's only jumping from 1 to 2, because 10 to the power 2 is 100. So it's much shorter, and even to get to 1,000, which is 10 to the power 3, is only counting one step further. And this is also a reason why our eyes and ears are calibrated logarithmically. So, and it makes it very efficient, because we can easily adapt with our eyes to brightness or darkness. So it only takes us a very short time to adapt to darkness when we come into a darker environment, because that is the amount of photons going down very quickly. But we don't have to count that much when we use a logarithm.
I've heard that the cochlea is also sort of spiral, isn't it? And it works
that's also a spiral, but that may be different, because this is related to 3-dimensional space in 6 different directions. So this is related a lot to our spatial balance.
Okay. Yeah.
Yeah. Yeah, so let's see what kind of numbers do we have. So we have those natural numbers, which are also called integer numbers, 1, 2, 3, 4, 5, 6, 7. And then we have very important numbers called prime numbers. And I didn't understand at school what prime numbers are and why they are important. So what they are, of course, these are the ones you can only divide by themselves or by 1.
Yeah.
This is a prime number, but why is that important? Nobody told me. I don't know. Did you hear that at school? I didn't.
No, and nobody ever said why they were important. They just taught you.
So there are prime numbers. Later, I learned when I was getting my education from Hartmut Müller for the scaling law that he discovered. He said that there are only prime numbers that exist. Because every number that is not a prime number is created of is a multiple of prime numbers. So the 6 is 2 times 3, and the 2 and the 3 is a prime number. The 5 is a prime number then again. 7 is a prime number, but 8 is 2 times 2 times 2. That is made of 3 prime numbers. So those kind of prime number factors, at the end it turns out it's only prime numbers that exist. So that's one thing. Of course, and then we already know what these prime number factors are. So we can divide numbers by 2, by 3, by 4, by 5, by 10. And then when we come to a prime number, we get stuck. We cannot go further. So when we come to, let's say, 68, divided by 2, it's 34. Divided by 2, it's 17. And then that's the end, because we end up at prime numbers. We will get back to this later again, because when we come from the other side, that we create something and start at 1, then there's always a different quality when the next prime number is coming in. That's also funny. So
1 isn't considered a prime, is that right?
Yes, that's what they say, because the number you divide it to is the same.
1.
It's always 1.
Yeah. Okay.
So that's a kind of an exception, but then it really starts with 2. But when we start with 1 and we create bigger cycles, then a prime number again will be important. We can also create ratios with numbers, things like 2/3 or 2/4. And then we talk about rational numbers.
Yeah.
And then we have irrational numbers. These are even more, because those numbers, they do not come to an end, like 2/3. That's 0.6 period, never ends. And then we have another type of numbers that is called the transcendental numbers. And we all know one transcendental number, which is the pi number, that we need to calculate with circles and balls. And there's another one which is called Euler's number E, and we will come to that back. And then there are other numbers, imaginary complex numbers, but we don't want to cover those for today. That is getting complicated. But let's go a little bit further now. So numbers are also describing how things are embedded into each other and how they relate to each other. So the 4 has embedded 2 times the 2. It's not only a square number, which we can use in geometry to create shapes, but also as a kind of scaling, because and scaling is always about embedding something. Or we find the 2 3 times in 6. That's also 2 times the 3 is embedded, 3 times the 2. And this is important when we talk about vibrations, because vibrations they also can relate to each other, and they can be divided and multiplied, like double frequency with half wavelengths. And we know this from musical octaves, for example. An octave in music is always doubling the frequency and dividing the wavelengths into a half.
Mm. Mm.
And then we have fifths, for example. This is 2/3. That's a relation of 2/3. Yeah, and so on. And by this, we experience something that we call resonance, that things are vibrating with each other. And then these resonances can end up in being consonant or dissonant. Yes, so something that is a harmonious relationship, and the dissonance is something that we don't see as a harmonious relationship because the embedding doesn't work. Yeah, we hear two things together and they dissonate because they are not embedded into each other. So the relation they have with each other doesn't fit.
Yeah.
So this is when we look at vibrations and relate it to numbers. Yeah.
Yep.
So yeah, let's go back and build things up from prime numbers now a little bit. Okay. So when we create something, we start at 1, let's say, create another one, and we have 2 cycles, which is the first prime number then. Yeah. And then we have doubled it, and then we add another one, and then we have 3, which is the next prime number. But this 3 has a totally different quality than the 2 had, because we can divide the 2 by 1 and 2, but we can't divide it by 3 without rest. So when we start counting to 3, there is a new quality because the divisibility by 3 is introduced now.
Okay.
That wasn't there before.
No, it's a new.
It's a new thing that hasn't been there before as a divisibility, and how you can put things into parts, and how the thing is made of. So let's add another one, and we get to 4. This is not something new.
No.
Because that's 2 times 2. We had this before. So let's go one step further to 5. And this is again a new thing. The divisibility by 5 is now introduced. Yeah. So that's why the prime number is always a next level of divisibility, which hasn't been there before. And this is how things can arrange each other in bigger systems. So there's always a new level introduced of how things can work together.
Yeah. Okay.
Yeah. So that's a little bit of fun of those prime numbers. Not only that it's only prime numbers that exist, but then if you build something, there's always a new quality which comes with that. And we have this slide here which shows the distribution of prime number factors.
Yeah.
Yes, and it starts on the left side with 1, and then it's only 1 factor, and then it goes to 2, and it's only still 1 factor, which is the 2, and then it goes to 3, and still 1 factor only, and then we come to 4, and it jumps up to 2 because we have 2 times 2, and then it goes back down to 1, which is 5. It goes back up, and so it just follows the amount of prime number factors And when we
I
look at the
understand that now.
graph, how it's created, then
Mm.
we can see in those little X-shaped things which I have created that the structure is repeated
Mm.
regularly. And there is a factor how we would see that. So that's a scaling factor in how the prime number factors are distributed. And this is a fractal.
So I have a question.
Yes.
I can see that the egg shapes increase logarithmically,
Yeah.
but what are they surrounding on this diagram?
Yeah.
Because they don't seem to be, are they just the first expression of a new quality, a new divisibility?
No, they show something that is similarly distributed. So when you look at the yellow graph, it's always going one up, and then it has two little legs coming after it. And then the next one is the same thing. One goes further up, and it has two which follow. And you can see the same shape in all four of them, which are here.
Oh, that I didn't get the first time I saw this.
So,
Okay.
so this is the repeating pattern. It looks a little bit like a church.
Yes, with a steeple and yeah.
So this is the repeating pattern, always a little bit magnified, and this is by the same factor, and then it creates a scale, and this is a fractal scale then.
Got it. Okay.
Yeah. So here we can even say that in the continuum of our natural numbers, there is a fractal embedded. But what does it mean? Many people just, I think, don't know. When you have heard about fractals, then people mostly know that this is kind of a mathematical thing where you can repeat the same mathematical method again and again and again.
Different
and they
scale.
call it an iteration. And then it creates, and this is due to Mandelbrot, that we have that fractal geometry with those nice fractal images, which we can see everywhere in nature. So we know that this is the same mathematical step that is repeated over and over again, and that never ends, and you can zoom in and out. And it's also known that we can see this in nature. But how does nature the math?
Okay.
How do we have that fractal structure in the circulatory system of all our organs? Which the branches of the artery of the kidney just look like a tree. And why are they similar to a tree? So how does our body know the math to do that? And now this is the time where we go back to our vibrations, because what is a vibration? Vibration is repeating the same thing again and again. In mathematics, this is called an iteration. In when we look at energy, at things that oscillate, we could call it an oscillation. So this is another proof for that in the number continuum, in our natural numbers, we find an oscillational pattern, which relates to vibrations and energy. And it's in our normal numbers. When we look at divisibility, and divisibility is something that is related to resonance.
Okay.
So 2 would resonate with 4, but not with 3.
Mm-hmm.
2 can only resonate with 3 when we look for the next multiply. So that would be 6, because the 6 is made of the factor 2 and the factor 3.
Yes.
So then 6 would resonate with 3 and 2.
Mm-hmm.
And this is very important for how things arrange each other in the solar system, let's say. Because when things resonate, they would start to exchange energy, and they might become amplified.
Mm.
And you know what happens when the orbital period of the Earth and the Moon would resonate with each other?
Mm.
It would speed up and we would get in trouble.
Yeah.
So it would lose its stability.
Mm-hmm.
That's what happens. So we always like to say, oh yeah, resonance is very important and this is the best way to communicate and exchange energy. Yes, that's true, but it's not true for systems that want to stay in a stable state.
Yeah.
Yeah, it's good to have that for a short time, but not too long.
Yeah.
Yeah, and we know this from bridge crashes, and we all know this thing when a singer can destroy a glass with a vibrating voice, or other machines could do that. So this is resonance, a kind of tricky thing. So we like it, but there is constructive and also destructive resonance.
Mm.
It's not always useful, so to say.
Okay.
Yeah, and our universe, the solar systems, the galaxies, we know that the Earth orbits the sun for the sun was created itself 4.5 billion years ago.
Mm-hmm.
And the Earth has nearly the same age. So they found a way to orbit each other without getting in trouble. So they have avoided resonance.
Okay.
Yeah, they found, and this is related again to ratios. So you have to find a ratio which would not resonate. Then things are stable.
Yeah.
And when we come from here to, let's say, irrational numbers, those are the numbers like 2/3 or 1/3 or 2/5 or something, or the square root of 2 is very famous. And another irrational number is the golden ratio, phi.
Yeah, heard of that.
Yeah, that's also an irrational number. And because they don't end, they never find a ratio really. And that's why they are called irrational. So they are avoiding resonance. Irrational numbers avoid resonance, but only to a certain degree. Because when we take the square root of 2 and we multiply it with itself, we have 2, which is a rational number. So irrational numbers still can create ratios when they are using some kind of algebraic method to change.
So square root of 2. So I'm going back to my maths now.
Yeah.
2 times 2.
No, square root of 2 times square root of 2.
So times itself, yeah, because I was thinking.
Itself. Yes.
Okay, yes, okay, is 2, yeah, which is a rational number, yeah. Okay, perfect.
And phi is a little bit the same. So it's an interesting ratio because when you have a line and you divide it in a part A and B, then the ratio A to B is the same as would be A plus B to B. So the shorter is in the same ratio to the longer as everything together is to the longer.
Yeah.
I've done that. That's the same thing. Yeah. And we find the square root of 5 in it, in that number. That makes it irrational.
Okay.
Phi is 1 plus square root of 5 divided by 2.
I didn't know that. Right.
Yes. And that's 1.618 and so forth.
Yeah.
And there's another interesting thing to phi. Because we can represent numbers as so-called continued fractions. So this is a fraction which is longer. So you could say 1 per 2 plus 1 per 2 and write it all down. We will see it on the slide here. And you know, when we have a natural number like, let's say 2, and we say 2 plus a half, that is halfway to the 3. So the denominator 2 is quite small. But when we say 2 plus 100, then this is only, so the first one was 2.5, 2.5. But 2 plus 100 is 2.01. So what we learn from here is the bigger the denominator is, the closer we come to the number itself.
Okay, yeah.
Yeah, so this is something we learn. And in a continued fraction, that's the interesting thing. When you want to, but the closer you come to the number itself, the closer you come to resonance.
Yes, of course.
Yeah, so the further you get away from the number, the less you would resonate. So it's about the denominator. The smaller the denominator is, the further away you get away from ratios. So the smaller that denominator is, the more irrational the number is. That avoids resonance. So what about phi? Phi is an irrational number. And when we look at it as a continued fraction, it's a continued fraction that never ends. And it consists only of ones. So the numerator is always 1. The denominator is also always 1. And the next numerator is 1, and the next denominator is 1, and it never ends. So it is the only one irrational number that is the most irrational.
It has the smallest denominator.
Right, yeah, because it's only made of ones. Yeah, and this because that is the smallest integer denominator which exists, and that avoids resonance the most
Oh, yeah.
of
Okay.
all irrational numbers, but we can still find a way of multiplying the square root of 5 with itself, so you can still make the phi a rational number in some way.
Mm.
And the phi is also still something else which is very important, because when we draw the continued fraction as a graph, it looks like a damped oscillation.
Yeah.
And it starts with minus 1.5, and then it goes up to, or not minus, but 1.5, and then 1 2/3, and then it goes back to 1.6, and then it goes up again, and it comes even closer to its value, but it would never reach it.
Yeah.
Coming closer and closer and closer, and the ratio between those numbers is then the phi ratio. And interestingly, many of us have heard about the Fibonacci series.
Yes.
Which is said to be seen in nature very often, and that's somehow related to how plants would grow, and then it creates the phi ratio, which we find very harmonious. We like it a lot. But again, the reason is it is able to avoid resonance quite well, and this is why it is used in architecture.
That was going to be a question.
Because when things do not resonate, they don't destroy each other.
Yeah.
By destructive resonance.
No.
And that's why the churches are there for many hundred years.
They don't get destroyed in earthquakes like other buildings. Yes.
Yeah. Because the inner structure is very quiet.
Yeah. Oh,
Yeah.
wow.
Of course, we like that because we are made of the same thing. Our body also wants to be stable.
Mm-hmm.
Yeah. And the Fibonacci series has even more things to tell us. It tells us how nature creates backups and memory.
Yeah, this is bit I was looking forward to, because I didn't quite get this.
This is really interesting. I just created a whole table here of all those numbers, and it all comes out with the Fibonacci series again. But it's you can easily explain it. When we do the normal, let's say, scientific series of things in how computers are made, for example, or storage memory of computer systems, then, you know, we all have 1 gigabyte and 2 gigabytes and 4 gigabyte and 8 and 16 and 32 and 64 and so forth. This is something where we always double everything. So we double the 2 and we get 4. So we double both. Then we double 4 and we get to 8. And when there is a mistake, the mistake is always taken to the next generation. Yeah, there's no backup. But in the Fibonacci series, it's different. In nature, we have one thing. Of course, you have to double that one. And then you get to 2. But then you don't double the 2. You double only one of them.
To get through.
And 1 is the backup. So what happens? 1 is doubling, you have 2, and 1 is the backup, and then you get to 3. And then you have 3. And then you take one again that you had before, and you leave it as a backup, and you have two that will double and will be 4. And then you have 5. So, and for the next generation of 5, you will double 3 and keep 2 as a backup. When the 3 doubles, it's 6.
Yeah.
Plus the 2 backups, it's 8. And it's always the next number in the series. So when you come to 8, you would save 3, double the 5, and you have 13. So, and it's easy to do because you always save the smaller amount of the one that was there before. Yeah. So in mathematics, it's called a recursive series.
Okay.
But you can always have a backup of the former generation and take it to the next.
Okay, I think I get that. I'm going to have to study
with all the information in it. Yeah.
Okay, right.
That's quite interesting, and I don't know if we should talk about it a lot today, but I only mention it. We can do that later if we wanted to. There is the scaling law that was discovered by Hartmut Müller that uses the number E, Euler's number, as the multiplicating factor, as the constant in the scale. And this is what nature really seems to do.
Okay.
And there is something that is called the square root of Euler's number E. And that one is very close to the value of phi.
Okay.
So this is how nature plays a little bit, because there are always little fluctuations. Yeah, so very often people say, oh, that is 1.648. That is the golden ratio because it's very close to it. Yeah, but maybe not, because 1.648 is the square root of Euler's number E.
Yeah.
And this is something that is a transcendental number which avoids resonance even more. Yeah, and now we come to transcendental numbers, one of which is pi. Pi 3.141. And the other famous number is Euler's number E, from which we all have learned the natural logarithm that is set to be natural because that's the growth factor in nature.
In nature, yeah.
Yeah, and this is on what the whole global scaling theory is based.
Okay.
On the natural logarithm. And transcendental numbers are different from irrational numbers. They avoid resonance even more because you cannot turn them into rational numbers.
Yeah.
Never. So whatever you do to them, they always remain or irrational or transcendental even. But Euler's number is even more special. Because we know when we have the exponential function, the E function, or the logarithm of E, that function changes from point to point. And that is called the rate of change. And mathematicians call that the derivative. And when you do the calculations for the derivative, it is again Euler's number.
Yes.
Yes, it's the same number, which is transcendental. So not only that the number itself avoids resonance, but how it changes in the rate of how it would change, this is also avoiding resonance.
Yeah, that's
And this seems to be the only number in the universe that does this. So this is the number which avoids resonance forever. We could probably say that. And this is how nature creates its stable systems that can live for billions of years, like we have them in the universe, or even atoms. Yeah. In an atom, we have electrons and protons. And when we look at their masses, they are about 1,800 times apart from each other. So a proton is 1,800 times heavier than an electron. But it's even another number. It's 1,836 point something. And when we look at this and take the natural logarithm of that ratio, it turns out that this is the 7.5 exponent of Euler's number.
Okay.
So it's Euler's number multiplied by itself 7 times.
Yeah.
And then multiplied with its square root. So then it is still transcendental, that number. And so the proton and the electron in the atom, they avoid destructive resonance so that they cannot collapse.
Just like you said with the Earth and the Sun.
Right, yes. Yeah.
Orbiting each other. You don't want them speeding up and crashing into each other. Yeah,
right.
okay.
Yeah, so this is how this Euler number is stabilizing many things in the universe. And the reason is it avoids that destructive resonance.
Yeah.
And on the other hand, we want to have a big resonance. So when we want to saw something, the size of the sawtooth wants to be in resonance with the material we want to saw, because we want to make it easy.
Yes.
And that's why the sawtooths have different sizes for wood and metal, for example.
Yeah, they do.
Yeah, because it's the inner structure of the material related to the size of the swords, and they should resonate.
I've never thought of it like that.
Yeah.
Amazing.
So this is what I want us to learn. We see those things in nature outside. But Euler's number is very interesting in general. When we look at its continued fraction, because every number can display it or as a continued fraction, then we would see that in the denominator we have all natural numbers starting at 1 and ending at infinity. And we have the same series of natural numbers in the denominators. So Euler's number includes in its inner structure the whole number continuum that ever exists.
Wow.
When we look at the natural numbers. And when we look at the ratios created in the inner structure, we see the 1/2 is an octave. We see the 2/3, which is a fifth. We see the 3/4, which is the fourth. We see the 4/5, that's the major third. So the whole musical scale, that harmony that we find everywhere in nature, is living in Euler's number.
It's extraordinary, isn't it, to think of that?
Yeah.
One number that can do it all.
One number, yeah. 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 That's really an interesting thing. And when we look at the consequences, when we have a scale that is calibrated with the Euler's numbers and its exponents, then we can do from number e to the power 0, which is 1,
yeah.
And then e to the power 1, e to the power 2, 3, 4, or e to the power 1/2, which is the square root of it. And then we can have a third, a fourth, and so forth. And these are all transcendental numbers. And because they avoid resonance, they create so-called islands of stability in the number continuum. And this is the same everywhere in the universe. On small scales, on big scales, it's always the same. And this creates and represents frequency ratios that avoid destructive resonance and create stable systems. And those islands become attractors, because stable systems want to organize themselves around them because they don't want to be destroyed.
Yeah.
Yeah. And so everything that attracts matter has its origin in the number continuum at the end. So also our bodies.
Yeah.
Yeah. And when we say that consciousness is always also the kind of awareness of the interaction between those attracting parts on the same scale, because it's all one, then matter, consciousness, and the resulting life has its origin in the number continuum.
Right.
At the end, all rising from prime numbers, which are certain periods of time or wavelengths.
Yeah.
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 The only difference how we count those. Yeah. And then we find some important oscillations, vibrations in the universe, which are basically kinds of metronomes that give the rhythm,
yeah,
of everything. And there are two of those really stable vibrations that are known. And one is called the electron, and the other one is called the proton.
I mean, the particular frequency of vibration of those two things.
Yes, because today those particles are seen as vibrational systems.
Yeah.
So there are standing wave oscillators.
Yeah.
And they are very, very stable because their lifespan, the lifespan of a proton, for example, is at the range of 10 to the power 32 years.
Yeah, which is a lot of years.
Yes, yes, that is at least 22 orders of magnitude more than the age of the universe.
Right.
So nobody has ever seen how a proton was created or destroyed. So we could say it's just there forever. And the electron is similar to that. And these are little vibrations.
Why
which are just always there.
Why do physicists persist in trying to break them apart then to create these sub-particles that they're trying to create or find?
Yeah, yes, they always, because they think there must be something smaller that created it. And that's true. The only difference is you can do it because when we live in a scale where everything is embedded into everything, then you would assume that the proton is not the smallest or the electron is not the smallest. There could be something smaller. And then they smash them with high velocity onto each other, and then they break apart. And you really need high energy to do that in an accelerator. And of course, you then see smaller things.
But they're not necessarily
smaller vibrations, but they only last for fractions of seconds.
Yeah, very unstable. Yeah.
They are very unstable. That's the difference.
Brilliant.
And probably the smallest thing which is there in our, let's say, observable universe, and even we can't see it because it's very, very small, that's what is called the Planck distance, for example. And when it is a distance, it is a wavelength. And when it's a wavelength, it is a circle, and it has a time period, and it has a mass. And that wavelength is the smallest, and it is 10 to the minus 35 meters. So unbelievable how small that is.
It's inconceivable to us. Yeah.
So it's just amazing. But that seems to be the smallest. But anyway, the two most stable oscillators is the proton and the electron, those two. And they make up all the atoms.
Everything. Yeah.
And this is why the visible matter is made of these stable things. And they are explanation why it is so stable. And it relates to the continued fraction again. Yeah, because those fractions, the fraction of an electron is very, very small. This is only one thing going up and down between two solid walls. So this is very, very stable. And when you have a longer tail, it just fluctuates and everything, but this one can only do this. It has not a lot of freedom, so it's very stable. If you have a longer chain, you can just dance around, but with only one pole between the walls going up and down, there's not much freedom. So you have a real high stability. And with the proton, and I can really not explain the exact mass for it, but the proton is so stable that it is the wall itself on one side.
Right. Yeah. Okay. Yeah.
And this is the reason why they could be seen as the two metronomes of everything that happens. Okay. And of course, at the end, the proton is more important than the electron because its mass is 1,800 times bigger.
Yeah.
It's smaller in space, but its mass is bigger. and that's why it also creates or is in a place where there is more density gradient, so there's more attraction to it than to the electron. But this is something for another video. I don't want to talk about gravity this time.
Let's not go into that yet.
Oh.
All right.
So we have seen how Euler's number is supporting stability in the atoms.
Yep.
Because it's a ratio between two stable oscillations. And then I've got some examples here, so and how things are related to each other. The heart rate at rest, for example, which is 67 beats per minute, compared to the breathing rate at rest, which is 15 times a minute. When we take the ratio of the two and logarithmize with the natural logarithm, it turns out that it's 1.5 or very close to it. And then it's again, it would say that it's e to the power 1 and a half. So that means it is the number e, Euler's number, and its square root. And they are both transcendental. So even physiology is stabilized by Euler's number in many ways. That was only one example. The Schumann frequency is the same thing. That 7.83 hertz in relation to the electron frequency, and then taking the natural logarithm is minus 46.04. So it's very, very, very close. So it meets an island of stability again. So this is not going to change. Yeah, and of course it wouldn't, because it depends also on the size of the Earth. So nature has arranged the size of the Earth in the atmosphere in a way that is very stable, that we can have living conditions which are quite constant.
Perfect.
And not changing all the time.
We should say the Schumann frequency is the vibration of the Earth. We haven't said that, but just for people listening.
Yeah, of course. So many people know it.
Most people do, but some people don't.
Yeah.
It just shows you why it's a stable.
It's a stable frequency that occurs in the atmosphere of the Earth.
Yeah.
Because of the size of the Earth and its atmosphere.
Oh, right.
Yeah.
Okay.
And nature has arranged it in a way that by itself it is very stable, which also means it doesn't need very much energy to keep on.
The lowest energy possible.
Yeah. That's another thing.
Beautiful.
So I did also something, because we have meridians in our body.
Yes, we do.
So, and then we have one day with 24 hours. And one meridian time is about, the active time is 2 hours. So we could compare 2 hours to 24 hours, which is the circle of 12 meridians.
Yeah.
And it turns out it is also very close to 2.5 when we use the natural logarithm. So this is also a very, very stable relationship here.
Yeah.
And again, we could also say 2 hours is 120 minutes. And then we can look at this, and it turns out it is, again, in the logarithmic world, it is 64.5. Yeah, compared to I think I have to look it up quickly. Compared to the proton, yeah, that's where it is. I wasn't sure was it to the electron or the proton, but it's a proton. Yeah. So there are so many interesting examples, and even the 24 hours themselves, they fall into the range of 67. So it's another island of stability, and it's always e to the power 67.
Yeah, okay.
So it's a very large number because the oscillation period of the proton is very, very small. So that's, I don't know, billions of billions of billions of fractions of a second. And that's why e on the power to the power 67 is a large, huge number. Yeah, but because we are using the logarithm, it's only 67.
Yeah, it's, as you said, it's
yeah,
easier.
So again, we can count very efficiently. So the next thing is 24 hours versus 1 week. That is close to 2. So it's more.
Another island of stability.
Yeah, it's another thing.
Wow.
And with the next one, this 7 days, the hours of 7 days is again something like that. So we figured it out somehow. That these are and that nature, yes, and we figured it out how nature did it, and use that counting that nature does itself. And it's all related to how cycles are embedded to each other, creating stability over a very, very long time.
Okay.
Yeah, because the lengths of the days did really not change over billions of years. So a year never has been 400 days or something. It's always very close between 265 and 365 and 366.
Yeah, and that's related to obviously the orbit around the sun.
Right.
So
and the fluctuation is not big, so it's quite stable.
Okay.
So this is also 69. And then I also looked at 3 weeks. This is another one. So 3 weeks is also a very stable thing. And another would be, it's a bit longer. So it's 33 days a month. That would be another island of stability.
Okay.
And so, yeah, this is just a little bit of a summary on that slide here, where I put together how the difference may be e to the power 1 or e to the square of the square root of e, or e to the power 3, or e to the power 1.5, and how this relates to 2 hours and 24 hours and a week and 3 weeks. And then we can do something which was not possible before, really. But when we think about numbers and islands of stability, then we can bring our biology into the cosmos, and we can do some kind of astral biology if we wanted to.
Okay.
Yeah. And then we can see how planets or other stars have resonance or effects on our body. And this could also imply when there were ETs who would come close to our solar system, and they would know the scales. They could measure the relationships of the planets in the solar system to each other, and they could find out how biological life could look like. Because the relationships in that system will be very similar.
Yes, I see.
Yeah, so
We could,
they could guess, and we could, if we go somewhere else,
if we could travel that
if we would be able one day, then
yes.
we could do the same, and then we would know better what to expect.
Okay. Yep.
Yeah, so that would be really interesting, and then we can take the weight of a newborn baby, which is 3.6 kilogram, related to the mass of the proton, and take the logarithm and find 63.
Which is another one.
which is another number, of course,
Okay.
yes,
Yeah.
in itself, but we can do something else. We can take the orbital period of planet Venus related to the oscillation period of an electron, take the logarithm, and also get 63.
Yeah, I see. So we're
And
embedded.
and then they are at the same place on the universal scale. So that means they would communicate. This is one thing. Yeah. And the other thing is knowing all these stable factors from outside. Those ETs that would measure, oh yes, this is the ratio of how planets relate to a proton or electron, and then somehow their biology would also relate to it in the same way.
Yeah, I've got you.
Because it doesn't happen only once. When we go to the main attractor 126 of electron stability and compare this with the mass of the Venus, that's 2 times 63. So we find it again.
Yeah.
Yeah. And then I took 30 minutes, half an hour, and proton stability, and that is also close to 63. So that's another cycle that relates to that scale.
Yeah.
Yeah, and this is just fascinating things which we could do in the future and learn about ourselves and our relationships to all the celestial bodies, and people would be able to explain even astrology.
That was one of the questions I was just about to ask you.
Yeah. Why does that all have an effect on us? So it's a configuration which is created, a pattern in space. Yeah. And of course, I think it's gravitational fields and consciousness that has an effect on parts of our brain, maybe, or DNA, whatever it is.
Well, if we're all in resonance.
Yes, of course, because this embedded. Is embedded again, right?
I think that makes perfect sense. I think we're going to have to wrap up shortly. So,
yeah.
Is there anything you want to sort of summarize our journey today? And
yeah, well, we probably have learned that numbers are real. That's one thing.
Yeah.
And they are universal.
Yes.
And they are symbols because we use them for counting all kinds of things. Yeah, we can count the numbers of protons, and we can count the numbers of electrons. Yeah, and the weight of a newborn baby of 3.6 kilogram is just a multiple of the protons. Of all the other atoms the baby's body is consisting of.
Yeah. Okay.
Yeah.
So
because we have billions and billions of atoms in that little body, and they all have their little weight, all these atoms, and they make up our body.
Which makes up the Earth, which makes up our...
And then we grow, we put more protons in. So we can't forget basically the electrons, because they they are only 1,800 times less in weight than a proton. So when we weigh ourselves, we always weigh the number of our protons.
Yeah, don't weigh the electrons, folks.
No, they're not. They're not really heavy.
They're not really heavy at all. So,
No.
so this has been fascinating. I thank you so much. And I know we're going to allow questions from people in the comments below. So,
yeah, I think this is very important. As we said before, we will even ask people to write their comments, write all their questions, and then we can probably set up something new and answer all these questions. So that would be very happy if we could build a conversation.
Yeah, I look forward to that.
I would love it. And then next time we could also look into fractals a little bit more and look into a little bit of geometry.
Oh yes, let's do that.
And yeah, and go slowly into the natural scaling.
And I thereby understanding the nature of everything, which is kind of what's coming to me. Is it explains everything. It's sort of this law that we've been looking for, isn't it, of the understanding, natural understanding.
And during this shutdown, people like Bruce Lipton, they were making videos.
Yes.
And he was talking about fractal evolution.
I saw it. Yeah.
And it totally fits. And and then I know that we both looked into Nassim Haraway's work.
Amazing guy,
which also relates to many of these things.
Yeah,
and then I also saw Rupert Sheldrake doing videos more than before.
More genetics,
talking about the same thing, and this is also something I would like, because there are quite a few people outside who talk about these things, all using a little bit different terms.
Correct.
And what I would like is to slowly teach people that look at this one and look at that one. It's basically the same thing what they're talking about.
Brilliant.
Yeah.
So we're here to bring it all together for you.
Yeah. This
all
is
right,
what I like. So yeah.
Thank you so much. We're going to leave it there. Please post your comments below and look out for our next video, and we'll see you soon.
Yeah. Okay. Thank you so much.
Okay.
See you soon.
Bye for now.
Bye.